This video will cover some of the basics of globular cluster characteristics, give some examples, talk about some of the uses that astronomers have made of globular clusters, and there's some extra resources at the end. So a definition of a globular cluster might be that it's approximately spherically shaped, the stars are gravitationally bound to each other, and typically they're found in the halos of galaxies, not in the disks of the spiral galaxies. This list looks a little long to me. We won't spend much time on any one item in this video. We're going to talk about the contrast with the globular and open clusters, how the globular clusters were used in the early 1900s to determine roughly the location of the Sun and the Milky Way galaxy, look at some images of globular clusters, talk about how globular clusters are important in helping astronomers understand the life processes that a star goes through. We'll talk about blue stragglers found in globular clusters, how the stars get sorted by mass in their position in the globular cluster, do some rough statistics, very minimal statistics on the counts of globular clusters for Milky Way and other galaxies. Talk about some of the categories of globular clusters in the Milky Way, and take a look at globular clusters around other galaxies again very briefly. So star clusters there are two big categories, the globular clusters and the open or galactic clusters. The globular clusters are much bigger, hundreds of thousands to millions of stars in this one object, a nearly spherical shape, as the object has enough gravity on its own to create this shape. The stars are not spread out as much as in an open cluster. We usually find the globular clusters in the halo of a galaxy or in the bulge near the nucleus, where the older type stars are found, and the globular clusters 10 to 13 billion years, most of them over 11 billion years old. We'll talk about how the age, at least one way the age is determined. Another characteristic is that there's a low abundance of elements heavier than helium, what astronomers call metals. They're calcium, carbon, oxygen, nitrogen, iron, etc. But low abundance, these are more pure hydrogen and helium stars than in the disk of the galaxy. So those are some of the big characteristics of the globular clusters. The open clusters have many fewer stars, much less population in the cluster, hundreds to thousands of stars, instead of up to millions that the globulars have. Because there aren't as many stars, there's not as much self-gravity of the system to hold it together. So the open clusters are more spread out, and they're disrupted after a period of time. They're not as long-lasting as a located body in space as the globular clusters are. They are found in the star-forming regions in the disk and spiral arms for a spiral galaxy, not in the halo. The stars typically are very young, hundreds of millions of years old, or perhaps a little bit older, but the cluster starts to get disrupted after this length of time. And there are more of the heavier elements present in the stars in an open cluster. So now more focused just on the globular. So there's a sketch of the Milky Way galaxy. We now know that the Sun is not at the center of the galaxy. The Sun's off to the side. We have the bulge, the nucleus of the galaxy, the disk of the galaxy. I think over half of the globular clusters are in this bulge of the Milky Way galaxy, and the others spread out around the halo. So there's a rough sketch. How did we come to know that the Sun is at its position? In the 1800s, astronomers from their star counts, had indications that the sun is at the center of this broad distribution called the Milky Way. That was a false conclusion, not realizing that dust and gas in the plane of the Milky Way was blocking our view of more distant objects. So in the early 1800s, Shapley had some inkling in the years before 1918 that it was strange that the globular clusters were found more in the what we call the summer constellations, Sagittarius and Scorpio, that the globular clusters tend to be found in that part of the sky. And he did a survey, a mapping. He was able to use a variable star in the globular clusters, a type of variable star, and estimate the distance to these galaxies, and then from photographs could plot where they're located above and below the plane of the Milky Way galaxy. And what he found was that the sun was not at the center of the distribution of the globular clusters. Shapley assumed that the globular clusters were orbiting the center of the Milky Way galaxy. So he was able to conclude that the center of the Milky Way galaxy, roughly in this position, the numbers down here are in kiloparsecs, but the scale is wrong for a couple of reasons. Shapley didn't correctly know the type of variable star he was studying, and then did not know about dust obscuring and making the stars look dimmer. Consequently, the numeric numbers on the scale here are not correct, but here's Shapley diagram reproduced in a Introductory Astronomy book from 1934. But it was a great step forward to realize that the sun was not at the center of the Milky Way galaxy, that the Milky Way galaxy center was at the center of a distribution of the globular clusters. So that was the first big use of the globular clusters. An example here from a ground-based telescope, a 20-inch diameter telescope, and we see the great concentration of stars towards the center. From this photograph, certainly, we cannot count the individual stars. 100,000 up to 300,000. I've seen estimates of the number of stars in this globular cluster labeled M13, Messier object number 13. It's in the constellation of Hercules in the sky, invisible. If you're in a dark location, you can see this just barely. And we have another view here with the Hubble telescope. So 36 light years across, pulls in most of this globular cluster, and hundreds of thousands of stars. The stars are much closer together in a globular cluster than they are in the region of the sun in the Milky Way galaxy. They're packed much closer together, and especially as you get towards the core of the globular cluster, the stars are extremely close together. I've seen estimates of 2 to 3 times the size of our solar system would be the separation between the stars. So much closer together. NGC 362, and this globular cluster is out in the halo of the Milky Way, and again it's been estimated to be over 10 billion years old for the age of this cluster. M55, also in the New Galactic Catalog 6809. And this particular one, I found a Hertzsprung-Russell diagram for the globular cluster, and want to spend a little bit of time here. The Hertzsprung-Russell diagram, the color of a star is plotted from left to right, and the blues are on the left, the reds are on the right. It's low temperature for the surface of the star on the right, high temperature for the surface of the star on the left. Dim stars are at the bottom of the scale, and the brighter stars are towards the top. The stars, the bulk of the stars, are on the main sequence for this globular cluster. If you were to pick a random star in the Milky Way galaxy, 90% of the time you would pick a star that's on the so-called main sequence, where a star spends most of its life. This globular cluster, estimated age 11 billion years, and the age can be estimated. One way to estimate the age is by locating what's called the turn-off point. So the main sequence continues on up in roughly this direction. The cursor is going up here. But the more massive stars, they do have more fuel, but they burn up this fuel at a tremendous rate. And it turns out they exhaust the hydrogen at the core of the star before the low-mass stars would do so. And those stars have left the main sequence. They've moved on out here into the red giant region, and some of them coming back here into becoming white dwarfs. A little bit too much information on the life stages of a star there, but the important part is that astronomers have calibrated where stars are leaving the main sequence, this turn-off point. They've calibrated this with the age of stars. And it's a little bit too technical to go into how they do that, but the calibration is trusted and indicates a age for a globular cluster. I'm going to comment just shortly about blue stragglers. So if the stars go through, the more massive stars go through their fuel first, their nuclear fuel, and move off here, why are these stars still being found in globular clusters, these blue stragglers? So that's not a completely answered question, but there is evidence that the blue stragglers being found more near the core of the clusters where the stars are closer together and collisions more likely. One theory is that stars are colliding and becoming massive again, and that extra mass, extra fuel, they are now hotter on their surface and bluer, brighter. So that's one possible mechanism. Another mechanism would be binary stars that are close together and eventually merge again to form a more massive star that is bluer for its overall color and is brighter. So blue stragglers, an interesting question on how blue stragglers come to be. Another example of a globular cluster, and Hubble, I think, at the bottom here, Hubble was able to measure velocities for 15,000 individual stars in this cluster. With the Hubble telescope, it's not just a blur of light, but individual stars can be imaged and measured. There's good evidence that the more massive stars kind of settle in to the center of a globular clusters, and the less massive stars pick up energy, kinetic energy from the more massive stars through their gravitational interactions as they pass by each other, and those less massive stars pick up speed and move to the outer regions of a globular cluster. The more massive stars kind of settle in towards the core of a globular cluster. Well, what about the Milky Way? Over 150 globular clusters have been identified, and there are probably some that are obscured by the dust and gas through the plane of our galaxy. As we look towards the center of the galaxy, we're probably missing some that are on the far side of the nucleus of our galaxy. The globular clusters, their orbits have been identified for many of them, and they have a random inclination. They are not moving in sequence or in concert around the center of the Milky Way. They're inclined, their orbits are tilted randomly to the plane of the Milky Way galaxy. Over half are in the bulge of the Milky Way, within 15,000 light years of the center of the Milky Way, so very roughly within half of the distance of the Sun to the center of the Milky Way galaxy. Our position is about double this distance away from the center of the Milky Way galaxy where the Sun is located. So there is a concentration of globular clusters towards the center of the Milky Way galaxy. The Andromeda galaxy, it's been studied in the space around the galaxy, and the rough estimates of perhaps 500 globular clusters being around the Andromeda galaxy. It is a larger galaxy than the Milky Way, has more gravitational force in the space around it. And then a study of M87, a giant elliptical galaxy that's bigger than both of the Milky Way and the Andromeda Galaxy. I hope I'm correct in saying that, but that's my memory. And perhaps over 13,000 globular clusters in association around the space nearby this M87 giant elliptical galaxy. So globular clusters are not rare, and they're useful for studying the development of galaxies, as the globular clusters are thought to, most of them anyway, to be very old and forming about the same time the galaxy was forming. So their characteristics are kind of fossils of the original material that the galaxy formed out of. So back to the Milky Way, astronomers have studied, with those clusters being closer to us than clusters around Andromeda or other external galaxies. The globular clusters in the Milky Way have the best studies. There appear to be at least two groups of these globular clusters. Some have extremely low abundance of elements heavier than helium. They're just hydrogen and helium and a few trace elements heavier than that. And then there's a group of globular clusters that have slightly elevated abundance of elements heavier than helium. Not as high as the abundance of these heavier elements in the sun, but there is a noticeable difference, a noticeable increase in the elements beyond helium in some of these globular clusters. That's somewhat evidence that these formed later and formed out of material that had been in other stars, but when supernova occur, those supernova events can enrich gas clouds with atoms that are heavier than helium in the periodic table. There's also evidence that some globular clusters may have been captured that used to be associated with other galaxies that got absorbed by the Milky Way galaxy. And there are even some suspicions that some of the globular clusters are the leftover bulge from captured galaxies that merged in with the Milky Way. Here's a photograph of globular clusters near M31. These bright objects here, these are stars in the Milky Way galaxy that just happen to lie in the same direction as this globular cluster. But again, globular clusters in other galaxies also have this spherical shape and a concentration of stars towards the center of the globular cluster. Here is a cluster of galaxies. So the larger globs here, those are galaxies, but the kind of snow, and I don't know if you'd call it static, but specks in the image here, those are globular clusters in this cluster of galaxies. And this cluster of galaxies, of course, these all haven't been counted, but from counting globular clusters in a certain area and take some other sample areas and count the globular clusters that are there, there may be 160,000 globular clusters in this cluster of galaxies. All the big lights you see in here, big images, those are galaxies themselves. And detailed, enlarged photographs of enlarged images will show the globular clusters, these smaller dots that are in view here. So certainly globular clusters are common in our universe. If you want to do some more of your own reading on this, somewhat technical book by Ashman and Zepp from 1998, but good information about research going on, a review of the research at a time period of 1998. Looking up in Google Scholar about globular clusters, I came across a very nice paper, Absolute Ages and Distances for 22 Globular Clusters using Monte Carlo main sequence fitting. So this is getting into the turnoff point technique, but Astrophysical Journal from 2017. And then a nice survey article in Wikipedia that you might want to glance at for background reading. Another aspect that I'm kind of just curious about would be the orbits of globular clusters, and that paper that I pointed out in Astrophysical Journal it also had information on the orbits of globular clusters, and using studies of proper motion and radial velocities, a little more technical terms I'm using here. So if you're in introductory astronomy, don't pay too much attention to this. If you're in undergraduate astronomy, getting towards advanced courses, you should know about proper motion, definitely. But there's a table: distance from the sun, distance from the galactic center, how close the globular cluster goes to the galactic center in its orbit, and how far away the globular cluster goes in its orbit, and how far above and below the galactic plane that it might be. So nice article. I'm going to go back and read this to learn a little bit more about the orbits of globular clusters. So it's a little longer video than I usually make, but you'll find short lecture and sample problems for physics and astronomy at these websites. These are free, no registration. At the website, you'll find the name of the video. They're organized in categories, so hopefully easy to find. How long it is, the description of the content, and then there's a link to the YouTube video you can click on. If you do somewhat enjoy these videos, please subscribe. Click on the subscribe button to my YouTube channel. Again, that is free.